Welcome to MathChat, the live call-in show that answers all your questions. I'm Frank Morgan, professor of mathematics at Williams College. My co-host is Eric Watson, a mathematics major.
Good evening, Professor Morgan.
Eric?
On camera tonight is Aaron Dupuis. Aaron, next week, what do you think about being Professor Morgan's co-host? How's that sound?
Aaron, my co-host next week.
He said yes. That's good.
Okay, we'll have Aaron on as co-host next week. Upstairs on Mixer tonight, Charmaine Mongram as usual, and Liz Claflin. We've got a big night tonight. In fact, a big week coming up. Do you know that? The mathematician Susan Lepp is in town. She's going to be giving a talk tomorrow at Bronfman Science Center at 1 o'clock.
What's she going to be talking about? Do you know?
There'll be another talk. Well, it's about the completion of number systems. So, good math topic. There'll be another talk on Wednesday. A lot of people might be interested too. One of your fellow students, Jerome Williams, is giving a talk on a proposition to end America as we know it, Wednesday at 1 in Bronfman Auditorium.
So anybody can come to that, right?
Anybody can come to this.
No prerequisites for math.
Anybody can come to that. Okay. And on Saturday, next Saturday, the Student Symphony has a lot of math majors in there, including the director is a math major. So there's a lot coming up this week, and I've been thinking about cans that hold food.
Okay.
You notice? Nice mass shape. Look at this thing. A big cylinder.
That's more of a drink, though. That food or
That's
drink.
A kind of food. You know, a drink is a food.
Right.
Drink is a food. And so I'm kind of interested in what the audience can find, the can of the largest food volume at home, and then maybe looking for cans that have the most efficient shape. We'll be talking about that more later tonight. But I want to get right to the calls, so let's get that phone on. Yeah, this can looks like it has a good shape.
Phone is on. Go ahead and call 458-0900.
We've got a little raisin can here. You know, raisins come in cans. Now, by the most efficient shape.
Hello, live on MathChat. Go ahead.
Hi, I called in, or I wrote a letter to you last week about asking if 3 salesmen went into a hardware store.
Oh, that was that good. That was that good. Yes. What is your name?
Jessica.
Jessica, right. We had fun with that question last week, didn't we?
Yeah.
We did well with it, I think. The question was, how long do you have to wait until they're all in the store again? If one comes every, what was it, every 4 days and every 5 days and every 10 days, I think.
Right.
Did we get the answer right, Jessica?
What?
Oh, you gave us the answer, didn't you? Every 20 days.
Yeah.
And then you heard our new one, which was, there was somebody who came every day, every 2 days, every 3 days, and so on up to every 10 days.
Right, and my question was, why does, you can figure it out either by listing all the factors or by doing prime factorization?
Right, or by doing prime factorization. So let's go back to that first example, which was every 4 days, every 5 days, and every 10 days, where 20 is the answer because it's a multiple of 4, and a multiple of 5, and a multiple of 10. And think about how we can do that using prime factors. So since 4, when you factor it down, is 2 times 2, any multiple of 4 is going to have 2 2's in it as factors. And since 5, that can't be factored, that's just 5, the answer is going to have at least 1 5 in it. And since 20 is 2 times 2 times 5, the answer is going to have at least 2 2's and a 5 in it. So when we look at all these questions, we see it's got to have at least 2 2's and 1 5, makes it 20.
But I was asking why it always works, because I understood how you do it.
But that's the reason, see, because if it's going to repeat, it's got to be a multiple, right, of the numbers?
Yeah, but the way, using prime factorization, you can...
And if you have a multiple of 4, it has to have 2 2's in it, right? 2 2's as primes.
Right, but then, you can list the factors and then write an equation.
And then if it has a 5 in it, it's got to have a 2 and a 5, right?
Right.
And so you just got to look back at all the numbers and say, how many 2's do we need? Well, because of the 4, we need at least 2 of them. Because of the 5, that we don't need any. Because of the 10, we need at least 1. And so altogether, which was the worst one? The 4, we need at least 2 2's. See, so that tells you how many prime number 2's you need.
Yeah, but how come it works with any number you always use?
Because with any number, you still have to have enough of each prime factor in order for it to be a multiple of all the numbers. So for example, when last week we were doing up through 10, how many 2's do you need to be a multiple of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10? Which number up from 1 to 10 has the most 2's in it?
8.
Yes. So that says the answer has to have at least 3 2's in it. How about 3's? Which number up from 1 to 10 has the most 3's in it?
6 or 9.
9 has 3 times 3. Very good. So we need 3 2's, 2 3's. Let's see what else. We maybe need how many 5's? What number up from 1 to 10 has the most 5's in it?
10.
Has just 1 5. Good. And 7's. What number has the most 7's in it?
None of them.
7 has 1 7 in it.
Oh, right.
So our answer is going to have 3 2's times 2 3's times 1 5 times 1 7. And if you take 8 times 9 times 5 times 7, then you get the answer that we got last week, 2520. And that's how you get it, using prime factors.
All right. Thank you.
That's great, Jessica. You might want to try a harder one sometime. How about this one? How about the numbers? What's the smallest number that's a multiple of all the numbers up through 12? So there's a new question, and if you want to call in, or anybody else wants to call in with that, Jessica, we'll talk to you or somebody else later, okay?
All right.
Thanks for calling in. Where are you from?
Williamstown.
Williamstown, and what school do you go to?
Mount Greylock.
Mount Greylock. That's one of our favorite places. We'll see what other schools we hear from tonight, but Mount Greylock's out in front so far. Thanks, Jess.
Yep.
Talk to you later. So there, now we're asking about the numbers 1 through 12. 1 through 12. That's going to get a little harder.
Hello, live on MathChat. Go ahead.
Hi, this is Bert calling with a question about probability.
Bert, on probability.
Burke.
Oh, Burke, right. Burke, you called last week. You're one of our favorite callers.
Okay. Well, I have learned that if you roll 2 dice, the number you're most likely to roll is 7, because that's the number with the most combinations of the 2 dice.
Yep.
7 is the most common number to roll with 2 dice. That's right.
What about 3, 4, 5, all sorts of other numbers of dice?
Oh, what if you have more dice? So here's a great question from Burke. Suppose you roll 3 dice. Suppose you roll 3 dice, then what number is most likely to come up? Burke, should we give this to the audience, do you think?
Okay.
We'll make it an audience challenge. If nobody gets it, you've got a prize coming. If somebody answers it right, they've got a prize coming.
Okay.
That's a great question for our audience. Okay, great. Thanks, Burke.
Oh, my sister's got a question.
Okay, good. Your sister's got a question. Good. Let's hear that, too.
Do you have any idea of what the Egyptian symbol for 1 billion is?
What the Egyptian symbol for 1 billion was that?
Yeah.
For 1 billion?
Mm-hmm.
The Egyptian symbol for 1 billion. This sounds tough. What's your name?
Sophia.
Sophia. What a question from Sophia. The Egyptian symbol for 1 billion. For 1 billion. I don't know that offhand. Can we give that to our audience too, Sophia?
Okay.
The Egyptian symbol for 1 billion. Oh, that's a good question. Okay. Thank you. What grade are you in?
3rd.
3rd grade.
And with the pyramids, did they have 3 sides or 4 sides?
The pyramids at their base had, how many sides? They had 4 sides to them, so they were square pyramids, whereas a lot of times today we like the looks of these triangular pyramids that have just a triangle at the bottom. Triangular pyramids are called tetrahedra, and square pyramids are called square pyramids.
Okay. Thanks.
Thank you.
Hey, thank you. Wow, 2 good questions there. I don't think anybody's going to get the Egyptian name for 1 billion. Do you think?
That I really
That
don't
is
think
really
so. That's a
hard,
tough one.
Sophia. Somebody might get the most common dice number. I don't know.
Hello, live on MathChat. Go ahead.
Yes, I have a question.
Okay, go ahead.
I was wondering, if you use Heron's theorem to find, well, actually, I know this already. This is a question for you. If you use Heron's theorem to find the area of a triangle with sides of lengths 20, 17, and 3, what happens and why?
So we want to use Heron's theorem to find the area.
Yeah.
We want to find Heron's theorem to find the area of a triangle with lengths 20, 17, and 3. What happens and why? So you're trying to stump us here, is that right?
Yeah.
And you've called before. Your name is?
Nico.
Nico, I recognize Nico. And Nico, what we've been doing tonight is leaving these questions out for the audience. Is that okay?
Fine.
And if nobody gets it, you've got a prize coming. Okay? Heron's theorem, the area of a triangle of sides 20, 17, and 3. Okay, great,
Thanks.
Nico. Thanks very much.
Okay, bye.
So Heron's theorem, I'm not even sure I remember that offhand, Eric. You know Heron's theorem?
No.
We've got a call here coming.
Hello, live on MathChat. Go ahead.
Hi, I've got a question.
Okay, go ahead. Who's this?
Noah,
Noah, yes, you've called before too, Noah. Hi.
how many digits in all the page numbers in a 1,000-page book?
How many digits in the page numbers in a 1,000-page book? Another great question here. I think we'll leave that for the audience too.
Yeah.
Another good question. I like that, Noah. That's lots of fun. How many digits in the page numbers? And Noah, does this start on page 1?
Yes.
Starting on page 1, okay, and going up through page 1,000. So for example, page 1,000 has 4 digits on it, right?
Yes.
So some of the pages have 1 digit, some have 2 digits, some have 3 digits. Got to figure out the total number of digits. Oh, that's a good question, Noah.
Now, Noah, is this something you've already figured out?
Yes.
Okay.
Okay, so we'll be able to tell then whether we get the answer right here or not.
Okay.
Okay, thanks, Noah. Good question. How many digits on all the pages? You know, pretty soon, if we don't get some answers, we've got so many
4
questions
prizes to give out
here.
already.
Got some, yeah, we may have to work on some of these ourselves, Eric.
Hello, live on MathChat. Go ahead.
Hi, this is Stuart Johnson calling. I'm at home here with Danae and Raina.
Okay, good. This is Professor Johnson from the Williams Mathematics Department with Danae and Raina, yes?
And they're in Pine Cobble School in 3rd grade and kindergarten.
Oh, good. Pine Cobble, 3rd grade and kindergarten,
And
yes.
here's a question that comes from Danae's homework.
Oh, good. A homework
From her
question.
homework. We modified it a little bit.
We better work on this one. We better have an answer for this one, I guess, huh?
It's a nice question. You're subtracting a 3-digit number from a 3-digit number.
Yes, a 3-digit number minus a 3-digit number.
You want the difference to be as small as possible. It has to be positive. You want it to be as small as possible.
A small answer, yes.
And you use the digits 0 through 9, and you can't repeat any digits.
0 through 9, and that you can't repeat any digits, and that has to give you the first number, the second number, and the third number. Is that right?
No, you just in the subtraction.
So we use 6 of the 3 digits from 0 through 9.
That's right.
We can use any 6 of them we want. The other 3 we don't need, and then we try to make the answer as small as possible.
That's correct.
Oh, another great question. Can we leave this for the audience too?
Sure.
Okay, we have a lot of good questions.
So with the answer, then the answer and the answer we get, can that be one of the 6 numbers we use?
Yes, that you can.
The answer can be anything.
Okay.
In the answer.
The answer could be anything.
Answer can be anything.
And the answer everything has to be positive though.
That's right.
And the answer, so the best thing would be if the answer were 1, if we could manage that somehow.
That's right.
But that's probably impossible.
I don't know.
Oh, he's not going to give us a hint. This guy is tough. This guy is tough. Are you this tough? Are you this tough with your homework, with your students, Professor Johnson? Do you ever give that? Are you this tough with your students? Can they ever get a hint out of you?
Never.
Oh boy, this guy. What are you teaching?
I'm teaching Math 210, which is differential equations.
Differential equations. This sounds really rough.
I am not taking that class.
Boy,
this
have you
semester.
taken this class?
I haven't, and I'm not going to.
And you're not going to
If
take
he's
that,
teaching it,
Eric?
no way.
Sounds tough, huh? What else are you teaching?
And calculus.
And calculus, which one? What semester? Beginning?
Beginning semester, my 2 favorite courses to teach.
Beginning calculus, beginning calculus. So if people want to learn beginning calculus, they might have to deal with Professor Johnson here. All right, we better let some callers call in with some answers. Thanks for calling, Stu.
Okay, take care.
Oh boy, have we got some questions here tonight. Let's review what some of these questions are. Hard to remember them all. What dice?
Hello, live on
most
MathChat.
likely?
Go ahead.
Hi, I'm wondering what a truncated hexahedron is.
A truncated hexahedron. A truncated hexahedron. So a hexahedron, of course, is a polyhedron with 6 faces to it. With 6 faces to it. And Eric, you know there's a famous polyhedron with 6 faces. Do you know what that is?
No.
Sure you do.
Am I supposed to know?
Sure you do.
me take
We've
the-
heard about it tonight from one of our callers. One of our callers was talking about hexahedra by the name of dice, little cubes.
Well, let's maybe take the dice.
Little die, right?
So that's one of the questions we have out there tonight.
A die. We have the dice question going. We're going to try to settle this one here. So a die has 6 faces to it, so it's a hexahedron. And truncated means that you slice off the 8 corners, leaving little triangles there. So that's a truncated hexahedron. It's a cube with the corners sliced off, exposing little triangular faces. Yeah? Is that good? What's the name of this caller?
Taboo.
Taboo.
Oh, Taboo. Should have known should have recognized you, Taboo. So do you like that? Now, what I'd like you to do sometime, Taboo, is see if you can find one of these. If you can.
Well, we have up a poster in our classroom of all these truncated and all these really weird shapes that half the kids can't pronounce.
Truncated. Taboo, it would be easier if we just called it a truncated cube.
Oh.
Wouldn't that be easier? And it has a special name if you cut off the biggest corners possible until the corners bump up against each other. And then you know what the truncated cube is called when you go that far?
No.
It's called a cube octahedron. It's called a cube octahedron. So there's another name to tell. But anyway, I'd like to see one of these models. If you send me a truncated cube or truncated hexahedron, I'll send you a prize.
Ooh.
Okay? Okay. Thanks, Taboo.
Bye.
Talk to you later. Yeah, dice are hexahedra. Did you ever know that's one technical name for dice? Or you could call them little cubes. Or you know what else you could call them? No. Dice.
Hello, live on MathChat. Go ahead.
This is Cyrene.
Cyrene, hi, Cyrene. Yeah, and always, you're one of our favorite callers, been calling regularly. What can we do for you tonight?
When I look at a spoon, I see myself, why am I upside down? When I turn it around, I am up, right side up. Why?
So you're saying when you look in a mirror, how come you're switched
She's looking at a spoon.
in a spoon? You look in a spoon, is this right?
Yeah.
And what happens when you look in the spoon?
I am upside down.
You're upside down in the spoon. And is that it, Cyrene?
When I turn it around, I'm right side up.
And when you turn it around and look at the back of the spoon, you're right side up. Is that it?
Yeah.
Oh, this is kind of tricky. You want to handle this one, Eric?
I think she's upside down to begin with.
No, Eric. Eric's a magician, you know. So he would do this by magic. But I think what happens in the spoon is that when you're looking in the spoon, the curvature of the spoon means that the light that goes to the top of the spoon gets bounced down, and the light that goes to the bottom of the spoon gets bounced up and turns the image upside down.
Okay.
Do you like that, Cyrene? Does that sound okay?
Yeah.
Well, Cyrene, though, that was such a good question. We're going to send you a prize. Is that okay?
Yeah.
That was a great question. You've got a prize coming, Cyrene.
Okay.
Okay? Thanks for calling.
Hi.
Bye.
Bye.
So that was good.
That was Cyrene.
She turns the spoon around, and then if it's curved
Then it
the other
looks
way,
right
then
side
it's no
down.
problem.
Then it continues to send the light that hits the top farther up and the light on the bottom farther down. It doesn't
Hello,
travel
live on
down
MathChat.
anymore.
Go ahead.
Hi,
should've brought a
this is Taboo
spoon.
again.
Taboo calling back.
Oh,
Go
Tom
ahead.
is back. Good.
I've got a math question, and I know the answer to this.
Oh, you want to try to stump us. Okay.
You have an archer, and the archer is hitting, the bullseye is 20, and then there's 19, 17, 16, 15
On the target?
yeah.
Okay.
And he wants to hit 99 points in 6 shots. How does he do this?
Okay, so you have the archer. Does it matter how far away the archer is?
No.
Okay,
So here we go. Numbers from 16 to 20, and he wants to hit a 99. How does he do this? And should we leave this for the... Oh, maybe we'll talk about this a little, Taboo. So if he hit the 20 all times, that wouldn't work. That would give him 120.
Right, so we have to come up with 20 less.
If he hit the little one, the 16 every time, he'd come up with 96.
So it'd be short.
So he'd be short by 4.
Right.
So if he hit all 16s except 120, that would give him 100. Or he could...
But
Or,
we need 99.
that would give him 100.
Okay.
So if he hit all 16s and a 19, that would give him 99. Or he needs 3 more than 6 16s. Or he could hit 3 16s and 3 17s, I guess.
Yep.
And that's a good one, because that way you don't have to be so accurate. You just aim in the 16, 17 region, and it's more likely you'll get a lot of 16s and 17s.
Yeah, and my dad has a question too.
Okay, good. Let's hear from your dad.
Hello,
Hi.
this is Tabu's dad.
Tabu's dad. Do you have a MathChat name?
Yes, Brian's brother.
Brian's brother. Okay, that's a good name. Brian's brother.
I'm having a birthday tomorrow.
Birthday
And
tomorrow.
It occurred to me that my age, as of today, is the product of a prime number and a prime number squared.
So it's a prime times a prime squared. So for example, you might be 2 times 9 or 18.
Something
Or you
like
might be 2 times 25 or 50.
What I realized is tomorrow I'll be a year older, but my age will again be a prime times a prime.
Oh, isn't that a great question for you,
The
audience?
first time it's happened, it feels different somehow. So I wonder if any of your listeners can figure out how old I am.
That's a great question, Brian's brother. We're going to put that out to the audience there. Your age today is a prime times a prime squared.
Right.
So it might be like 2 times 9 is 18, but then 19 isn't another prime times a prime squared, so that's not it.
Right.
The audience can look for this. That's a good one. Thanks, Brian's brother.
Thank you.
Boy, don't we have a lot of good questions tonight. Nobody's called in with cans or the dice answer,
Hello, live on MathChat. Go ahead.
digits and the pages.
This is Nicholas DeVoe.
Nicholas, hi.
We have 10 fingers and we count by 10. How could you count with just one finger?
So we have 10 fingers, so we count by 10. If you had just one finger, I guess you'd count by ones.
Or you could count, you could use binary, you could use ones and zeros, I guess would be one way of doing it.
Or you could draw with your finger in the sand.
That's true.
1, 2, 3. That's true. So do you want a real answer, Nicholas, or do you want an Eric type answer? So Eric's type answer would be you could count by using your finger to draw in the sand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My answer would be you ought to count by just numbers of fingers. So 1 is 1, 2 is 1 plus 1, 3 is 1 plus 1 plus 1, 4 is 1 plus 1 plus 1 plus 1.
Be tough to count that way.
And you wouldn't have any real number system. You just have to make however many marks you needed.
Yours.
What do you think, Nicholas?
1 plus 1 plus 1.
Yeah, I think that's the
Excellent.
best answer. I agree. I was better than Eric on that one. And you know what? As a result, Nicholas, see if you think this is fair. As a result, I'm going to open this little raisin cane here, and I'm going to reward myself with a raisin. Thank you,
And
Nicholas.
how old are those raisins, Professor Morgan?
They're good raisins. They're good raisins. I just brought in the can. I put the rest up. Okay, thanks, Nicholas. Talk to you later.
Bye.
Bye-bye.
Very juicy, delicious raisin
Oh,
here.
I'm sure they are.
Maybe you'll get a question later tonight. Hungry, aren't you?
Yeah. Hello, live on MathChat. Go ahead.
Hello, this is Ragnar.
Ragnar.
Go ahead.
Hi, and I was just calling, well, we learned this in math class, that it's impossible to have a triangle with sides of 20, 17, and 3 because it would be a straight line.
Oh, Ragnar, you got it. You got the answer to Nikos' question. Remember, Nikos called and said, what's the area of a triangle with sides 20, 17, and 3? And Ragnar points out that couldn't be a real triangle because the two of the sides together aren't any longer than the third side. And to get back to where it started, they would just have to follow the original line, and you'd just get a line with area 0.
Yeah.
Instead of
Right.
a triangle like that would look like this, it would just be a straight.
Just be flat.
line.
Just be flat. 2017 and 3. Of course. So that's a good illustration here. But Nico, I think, still wants to know why or why not. What happens if you try to use Heron's theorem? So we'll still need, if anybody wants to take away Nikos' prize from him, someone will have to explain Heron's theorem. But you've won a prize there for yourself, Ragnar. And if you call after the show and leave your address, we'll send you it.
All right, thanks.
Okay.
Thanks.
Good going. Ragnar got that one.
So we got some callers coming back trying
That
to
was
answer
good.
some of the
That's
questions.
good. I'm
we've got.
glad we're getting some answers back here. We don't have the number of digits.
Hello,
in the
live on
1,000-page
MathChat. Go
book
ahead.
yet.
This is Tyler.
Tyler, yeah, hi. How you doing?
Pretty good. I have an answer to the question where you try to take the 6 numbers and get the smallest number by subtracting them.
Oh, okay.
The 6. You do?
Yes.
Oh, Tyler. All right. So this was this question. All right. So what's your answer?
We got 14,
14.
and we have 412.
412.
Minus 398.
412 minus 398 certainly gives you 14, and unless someone can call up with a better answer, or unless Professor DeVoe calls back to say that's not the best answer, you've got a prize coming, Tyler.
All right.
And Tyler, I think I have your address from before, don't I?
Yeah.
Okay, well make sure you get it. Good going. 14. 14 is Tyler's candidate answer for that problem from Professor Johnson.
Right, so that's good.
Well, it's sort of nice to see someone beat Professor Johnson tonight, don't you?
He always
think?
liked to
He was
beat
kind
the
of rough,
professor.
you know?
That's
Well, he was kind of tough.
wouldn't give us any hints.
Wouldn't give
Hello,
us
live
any
on
hints.
MathChat. Go
I don't know
ahead.
who he would help.
Hi, I have an
I
answer
see
to
him
the
every
dice
day.
question.
An answer to the dice question.
Oh, good, an answer to the dice
Who's
question.
calling?
Rhiannon?
Rhiannon?
Rhiannon.
Oh, Rhiannon.
Okay, go ahead.
I think the answer is 9.
You think the answer is 9 because you can get 9 lots of ways, huh?
Mm-hmm.
You can get a 9, you can get 9 lots of ways, but 9 isn't quite right, I don't think. 9 would be like if you had 2 dice, you might have expected 6, huh? Using a 3 and a 3. But it's actually 7. And for 3 dice, what you want is something like 3.5, and so the best 10 or 11 is the best, because 3.5 plus 3.5 plus 3.5 gives you 10.5. And I think 10 or 11 is best. So not quite, Rhiannon, not quite, but I think I got the answer just in time that we won't have to send a prize, back to the dice.
Burke.
Burke.
Burke,
We
yes.
won't have to send a prize back to Burke, I don't think. And I can't believe it, but our show's over, Eric.
That's it?
Our show is over for tonight. So until, if you've got more things to say, folks in the audience, you can always call, send me mail. We can't take the calls. I'm sorry, everybody. Frank Morgan at Williams College. You can write to me there, or you can send me email at frank.morgan@williams.edu. And until next week, when Aaron Dupuis will be my co-host, this is Frank Morgan
And Eric Watson.
saying save up your questions for the next edition of MathChat.
That's lots of good questions.
Did we get great questions tonight?
Thank you.